This is the second lecture of the course Cognitive Modeling. My name is Afra Ali Shahi and I'm the instructor of the course. In this lecture, we are going to talk about modeling expectations. What do we expect from a model that's supposed to simulate a particular aspect of human cognition? I want to start by reminding you of this diagram which shows how an experimental study tries to study a cognitive process. If you remember from the previous lecture, we discussed that the cognitive process is usually being performed in a context of the environment it is situated in, and it receives certain stimuli as perceived by the human brain, and as a result of this process, a certain behavior is generated. Now, when we want to study a cognitive process in an experimental setup, what we typically do is we are trying to control the stimuli and then observe how the behavior changes as a result of this control. In a modeling study, in contrast, what we do is we are implementing the cognitive process using computational tools and techniques. We are simulating the input that the process receives, trying to make it as similar to the actual input from the environment as possible, and then the implemented process generates a certain behavior as a result of this simulated input. So, what exactly each of these methodologies give us? In an experimental investigation, what we do is we are trying to very carefully control only one aspect or property of the task or the input that the human subjects receive, and we want to see how this manipulated factor affects the behavior of the human subjects by studying a large group of participants. There are certain advantages that come with this methodology. Most importantly, it allows us to isolate different factors in the stimuli and then to examine the significance of the impact of each factor on the process. However, there are certain disadvantages to this methodology as well. First of all, it's only the input and not the process itself that's under our control. We cannot really change anything about the learning mechanism or the processing mechanism that humans use because this is an unconscious process and therefore it's out of our reach. More importantly, each object that comes into the lab has a history in this particular domain we are studying. For example, if you're talking about memory, human subjects that come to the lab, even children, already have been exposed to a lot of stuff, so they already have memorized things. Or if you're studying language or vision, humans typically have been exposed to perceptual or linguistic input in advance of this experiment, which might affect their performance in the particular task we are giving them. And this history is out of our reach also. We cannot really control that. However, when we simulate a process, when we study a cognitive process using computational models, we first of all have to come up with a very detailed specification of both the input properties and the mechanism itself, the processing mechanism, which gives us certain advantages. First of all the biases or constraints of the characteristics of the input data and the learning mechanism have to be specified in advance. Therefore, we know exactly how things happen and why certain behavior is observed. And we also have full control over the input that the model receives in its lifetime. So each human subject is basically the equivalent of a particular simulation, which is totally under our control. Also, we can manipulate the mechanism itself, and then we can immediately observe how the behavior changes as a result of the change in certain factors that concern both the input and the learning process. Finally, we can simulate novel situations and then try to predict what comes in situations like this. So I hope that you can see that experimental and computational modeling can be used as complementary methodologies, not to replace each other, but to give us a more complete picture, because each of the methodologies has certain advantages. And that's an important point to keep in mind in the rest of this course, because we are going to study the experimental studies as well as the modeling attempts hand in hand. Another important factor to keep in mind is when we are building a model that's supposed to study human cognition, then we have to make sure that the model itself is cognitively plausible. This means that the model has to adhere to certain constraints that humans face when they are performing tasks. For example, the input data that the model receives has to be similar to the real data that humans receive in all aspects. If the data that the humans receive is very noisy, which is most of the times the case, then the input that the model receives has to be noisy too. Otherwise, the claims that the model makes are really not ecologically valid. Also, humans face certain memory and processing limitations when performing tasks. It's not the case that they can remember every past experience, for example. And if a model actually relies on having access to all the data that it has seen in its lifetime, then it really cannot be seen as a cognitively plausible model. Similarly, humans process data incrementally. They have a particular experience, they process the data, they update their knowledge, and then they move on. And this is a process that has to be mimicked when building a cognitive model. A cognitive model cannot jump into all the data that it has received in the equivalent of the past 5 years and then try to come up with some optimized knowledge, which is the case for many of the commercial systems or applied systems. But if you are trying to explain how humans do things, then you have to follow the same kinds of limitations that they face. Okay, now we said that when we build a cognitive model, we usually have to base it on an existing theory. So there's a theoretical account which is trying to explain a cognitive process. These theories are usually stated at a more general, more high level, and as a result, more vague level. So the model has to specify the details to the point that it can actually simulate the process. And then we need an evaluation scheme that comes with our modeling attempt in order to decide how accurate the model is and how close it is to how humans do things. Now, as I said, theories usually provide a high-level characterization of the model, whereas models of a process, whereas models have to make certain decisions about the unspecified details of this theory as well. So when we look at models as an information processing task, we can usually study them at different levels of abstraction. A very influential distinction of these levels was proposed by David Marr in 1982 when he suggested that cognitive models must be understood at 3 different levels. The level of computational theory, this is the level that is basically concerned with what knowledge is computed. The level of representation and algorithm, this is a level that is concerned with how these computations take place. And finally, the lowest level, which is the hardware implementation level, how these algorithms are actually realized in the human brain. So let's look at each of these levels in more detail. In the first level, in the most abstract level, we are concerned with the computational theory behind the model. What is the goal of the computation? Why is it appropriate? What is the logic of the strategy by which it can be carried out? In other words, what does the model claim in terms of the information and the knowledge that's used by humans to perform a particular task? When we move to the next level, we are actually talking about specific choices that are being made in terms of the representation of the input and the output, and the algorithm that is trying to transform one of these to another, tries to map a certain input to a certain output. In other words, we are concerned with how the computational theory can be implemented, what is the representation of the input and output, and what the what is the algorithm for the transformation. Finally, if you're interested in the implementation level, in the most fine-grained level and lowest level of abstraction, we are now looking at the details of how the algorithm and the representation are physically realized in human brain. What is the architecture of the brain, or the portion of the brain that's involved in the cognitive process we are interested in, and how the details of the representation and algorithm are implemented actually. So, as an example, if you go back to the categorization model that we used as a simple example of what a model looks like, when we are concerned with the computational theory, we are asking questions like this. What kind of knowledge is computed? Is size relevant? Is shape relevant? Is color relevant? Are objects or concepts grouped together based on the function that they take on? When we are talking about representation and algorithm, we are more concerned about how computation takes place. So, questions like this. Are we first arranging objects into groups of two? Is there a hierarchical categorization that's being formed? So you see that we have moved from the state of the type of information that we use to actually how we process this information. And then, if we are talking about the implementation level, we are basically concerned with the architecture of the neurons in human brain that perform the categorization task. So, what if we build a model and then it's flawed? So the model itself is implemented based on a theory that makes certain statements at a computational level, right? The theory is usually stays at a more abstract level. It only is concerned about the types of knowledge that are useful for the task. But because we want to model this process and we want to run the simulations, we have to make decisions about, say, algorithmic level as well. So we have to add some details about the exact processing that has to be specified. So it could be that the theory itself is actually accurate in light of how humans perform a certain task. But these details that we added to the model are actually not cognitively plausible, or they're not compatible with how humans do things. So in this case, we actually have to study the model only at the computational level if the model is an accurate representative of the theory that we are interested in. And the algorithmic level details are actually beside the point. We just had to add them in order to simulate the process. So it is very important that a computational model specifies which level it is attempting to aim when simulating a process. So if I'm building a model of, say, how I detect edges in a picture, it is very important that I specify in advance to people who are looking at my model what level of abstraction I'm aiming at. What are my claims? Where are my claims? Am I claiming that a certain kind of representation is used? Am I claiming that my algorithm is actually the same thing that humans use when detecting edges? Or am I only claiming about the kind of information that's useful, for example, the contrast between dark and light regions, and that's what this process needs? Therefore, a computational model must be also only evaluated based on the level at which it attempts to simulate a process. So this is a very important thing to keep in mind when we are evaluating computational models in the future. Another important point to keep in mind when evaluating models is that performing better is not always a good thing. So when you are building a commercial system, for example, for translating a text from one language to another, and you want to sell it to people to actually use it as a tool, you really don't care about whether the system uses the same kind of techniques that humans use, right? What you care about is whether the system does a good job. So you are aiming at improving the performance. However, the goal of a computational cognitive model is to explain how humans learn and perform in a cognitive domain. Therefore, unlike the commercial systems, we want a model to not only explain how humans do things in a good way, but we also want the model to explain the mistakes and limitations that humans show. So if there is a general trend that humans make a mistake, for example, an optical illusion that you can observe in most humans, then your model of perception has to actually make the same kinds of mistakes. And so that's what part of the feature of the model. This is part of this is a desirable characteristic of a computational model. Therefore, the gold standard is human behavior. The question we are concerned with is how close is the performance of our model to that of humans? So when evaluating a cognitive model, what we need to do is to look at how they perform and then look at how the performance of our model imitates that. This is an interesting point because we really don't have access to the knowledge that humans acquire. The only way we can assess this knowledge is by looking at how they use it in certain tasks. So if we are talking about the domain of memory, for example, we want to see, does the model perform similarly to humans in recalling past experience? If we are talking about language, we are concerned with, does the model comprehend or produce sentences in a way that's similar to how humans do that? And if we're talking about the domain of perception, for example, we want to know how the model, to what extent the model mimics what humans experience when receiving sensory input. Okay, so this is all I wanted to say about evaluation of a model and what we expect from a model. Now, in the rest of this section, we will talk about the common frameworks in which models are built. So the next 3 lectures will focus on specific implementation frameworks that have been historically used.